In this chapter was the first part of an endocrine system, and as a reminder from chapter 7, we have two means of communications within our body. We have the fast means of communication using electrical impulses down neurons, and that's by the nervous system. And now we're going to talk about the slower means of communication using chemicals in the form of hormones through the blood. And this is why it's slow, because it has to travel from one area to another using our circulatory system. And this is going to be our endocrine system. Now also, longer lasting physical processes within our body, whether it's growth, development, all that's by this endocrine system. And as we saw as an example last time in this nervous system, if you put your hand on a hot plate, if you want an immediate response by your body, that's going to be the actions of your nervous system. And looking at this endocrine system, we use hormones, and the way hormones are secreted, they're secreted by what are called endocrine glands. And these are ductless glands, and this differs from what we saw from our skin, in which we saw exocrine glands. So this is from our skin and body membranes chapter. And with exocrine gland, let's just go over this first since we've heard about this before. We're going to secrete substances, chemicals, different secretions through ducts to the surface of our cells. So whether it's our skin, our cutaneous membrane, or within our stomach itself, our alimentary canal, in which case this can be a mucous membrane. So exocrine glands, these always go through ducts. Okay, so digestive enzymes also another example. Now, endocrine glands, these are ductless, meaning that they're going to secrete these chemical messengers in the form of hormones directly into our fluids, or our bodily fluid. And so we're just going to secrete them, and it's going to enter into our bloodstream. And let's see exactly how these hormones are carried from one area to the other. And so we're going to secrete them again directly into extracellular fluids. And who does all the work for us? Instead of neurons, we're going to use blood. And if you imagine, we have all these vessels that kind of serve as a communication highway between all the different organs and tissues within our body. Now what's going to happen? These hormones are going to regulate the activities of other hormones. And so let's look at a pathway. We're going to what's called a simple endocrine pathway. And what this is going to do is we're going to start off with a stimulus. So a stimulus is going to be received by our receptor protein. And that in turn, a receptor protein is found on our endocrine cell. On our endocrine cell, once we receive that stimulus, that's going to stimulate these endocrine cells to secrete their hormone. Now, we don't have those neurons. What we have is our blood vessels. So all of these hormones are going to enter into our blood vessels. It's going to circulate through our entire body until it finds our target cell. Whether it's going to be a tissue, a cell, or a membrane, it's going to get received by this target site. Once it's received at this target site, then we can create a physiological response, and this can be either mitosis, the secretion of downstream proteins, or whatever from the downstream target. Let's look at an example of this. So let's say in your body you just woke up or you just exercised. Now your body has low blood glucose levels. Well, we can receive this stimulus that you have low blood glucose levels by our pancreas. So our pancreas is going to receive the signal. We don't take in a lot of glucose as we screen our blood. So what are we going to release? We're going to release this hormone called glucagon. And we're going to get into what this hormone does. But the way I remember this is just in the word glucose is gone. That's why we're secreting this hormone. So this hormone is going to enter into our blood vessels. Here's this hormone, glucagon. And it's going to target our liver. And why is that? Well, our liver has a storage form of glucose, and it's called glycogen. And of course, we saw that in our chapter 2 looking at the chemicals. Okay, so once we target this liver, we're going to target glycogen breakdown. So glycogen is going to break down. That's going to get released into our systemic circulation. Now what happens? We can increase our glucose levels within our blood, and thereby we shut off this initial stimulus that we have low blood glucose levels. And this is exactly how the hormone system works, this endocrine system works. We're always going to respond towards some sort of stimulus. Now, Let's look at these effects caused by hormones. Okay, so here is that cell. Here's our surface receptor, and here's our hormone. Once this hormone binds to this receptor, what's going to happen to our cell? 5 things can happen. We can change the plasma membrane permeability or electrical state, meaning that we can make this membrane more permeable to glucose. So in the event we just ate a meal, we don't have a lot of glucose found within our cells, we can make our membrane more permeable to glucose, thereby allowing more storage there within our liver. We can have synthesis of proteins such as enzymes. Well, now let's say that we don't have a lot of glucose within our body. We have all this glycogen. What enzymes are we going to need? We're going to need to produce these enzymes to start breaking down this glycogen to free up all of this glucose. We can also cause the inactivation or activation of enzymes so that we can activate those. We can also stimulate mitosis, and this can specifically done by those growth hormones. Growth hormones can especially cause those bone cells, those osteocytes to grow and divide, giving rise to that elongation of your bones at that epiphyseal plate. And then here we have promotion of secretory activity. And so we can produce more secretions of mucose, more secretions of exocrine glands, or even more endocrine glands. Now there's 2 different categories of hormones that we can produce. We have amino acid base, which deals with proteins and peptides. And a couple of examples of these they could be amino acid chains. It can be insulin. So we need insulin. Some people who are diabetic need insulin shots. And another one is called antidiuretic hormone, which is a pituitary gland hormone. Okay, and we're going to get into that. It can also be composed of just amino acids, in which case we have 2 examples, epinephrine, and we have thyroid hormone. They can be lipid-derived, meaning that they are not composed of amino acids. They're composed of cholesterol, of steroids. Steroids specifically being made of cholesterol, and as an example for this we have testosterone. Prostaglandins, these are made from lipids, are highly active lipids. Because we have 2 different classifications of hormones, whether they're amino acid based or they're lipid derived, they're going to enter our cell through 2 different mechanisms. It can either be through what's called direct gene activation, or they can work and have their effects on the cell through what's called a second messenger system. So we're first going to start off with a direct gene activation, and this deals with our steroid hormone. And there's one concept you probably, if you've taken chemistry, you've learned and heard, is that like dissolves like. Oops. And what that means is that similar properties are going to be more able to integrate and interact with each other compared to properties that are very different. And for example, here we have steroid hormones. Steroid hormones, these are non-polar molecules. And if you remember our phospholipid bilayer is composed of what? 2 layers of phospholipids. That's why it's called phospholipid bilayer. And those are fatty acids, and a lot of those fatty acids are also non-polar. So remember, we have our polar head, but majority of our membrane is composed of this. The inner part of our membrane is composed of all these fatty acid non-polar tails. And because this entire middle region here is nonpolar, our steroid is also nonpolar. This steroid, and also surrounding here we have lots of those water molecules, which are highly polar. It does not want to be close to something like water that has all these charges and it's very polar. It'd rather be sequestered and enter into our cell where it's not polar. So it wants to cross through this membrane. And it can easily cross through that membrane because it's nonpolar. Now in our cell itself, we do have liquid, and so therefore it is another polar environment. However, because our membrane in itself is nonpolar, it can easily cross through that membrane and then interact downstream with proteins and other components in order for it to cause its activation and allow that hormone to have its effects on the downstream cell. And so this first part of direct gene activation, we're going to diffuse this hormone through that plasma membrane of the target cell. It can enter directly into our nucleus. From here, we have what's called, let's go back. We have a receptor protein. So this receptor protein is specific to the steroid hormone. So it's going to bind to its receptor protein within this nucleus. And what it's going to form what's called a hormone receptor complex. So the hormone and the receptor complex. Now, because it's formed in this state, we are now in its activated form of this hormone receptor complex. Now, because we form this activated state, this is going to bind directly to our DNA, to a specific site. And you remember, our DNA is this long, double-stranded form of genetic information. You can have instructions down here to encode one thing, down here another enzyme, here's another protein. Okay, now this hormone is going to bind specifically to that region of the DNA that can either cause things to happen, or it can cause proteins to be generated or transcribed, or proteins to eventually cause the inactivation of different activities, but it's only going to bind to a specific region of that DNA. From here, we're going to cause transcription. So remember, from DNA to messenger RNA, we have transcription. Okay, so we're going to activate gene transcription. And then finally, what's going to happen with this messenger RNA? It's going to come out of our cell. It's going to bind to ribosomal RNA. And this is going to be translation. So from that messenger RNA to a protein is translation. And so with direct gene activation, what's key to this entire process is that the steroid hormone can easily cross through that plasma membrane, because steroid hormone being nonpolar, plasma membrane also being nonpolar, easily can cross. It's going to act directly into and enter into our nucleus, complex with our receptor protein, cause a direct transcription of our messenger RNA, and then leading to our protein to be synthesized within our cytoplasm. Now the second form we have is second messenger system. This is for non-steroid hormones. And so this is when we have amino acid or nucleic acid based hormones. So amino acid derived. And because amino acids and nucleic acids, these are polar molecules, they cannot easily cross through this plasma membrane that is nonpolar. And so what does it have to do? Since it can't enter, it's going to have other enzymes do the work for it. And so what's going to happen is, here's our cell membrane. We have receptors specific to this hormone. Hormone's going to bind to a receptor protein along your cell membrane. And what's that going to do? It's going to cause a cascade of reactions to occur that's going to activate an enzyme also found along our plasma membrane. Now this enzyme can be found adjacent to it, or it can also be found within this membrane. So different locations for that enzyme. Now once this enzyme is activated, what's it going to do? It's going to catalyze a reaction that's going to produce what's called a second messenger. And so how does that do that? It's going to cause ATP to break down to ADP and phosphate, and releasing that energy. That's going to cause the second messenger to be activated, and this in turn is going to do all the dirty work for this non-steroid hormone, because the steroid hormone can't enter into the cell. So second messenger is going to carry out the reaction within the cell on behalf of the hormone. Okay, so what's that going to do? Let's see. It can have cellular effects causing glycogen to be broken down, as an example. It can also have additional intracellular changes. So what you should get, and we should gather from these two different pathways, are what type of hormone is it? Is it a lipid-derived or steroid-derived? Or is it nucleic acid or amino acid based? And how does it cause the activation of the cell downstream? Looking at this illustration to the right, we just saw how one of those hormones, when it binds to that receptor, or if that hormone enters into the cell, what happens downstream. Now we're going to look upstream more and see what happens and what stimuli actually cause the upstream endocrine cell to release its hormones to cause these downstream targets down here. And there's three different major stimuli of these endocrine glands. It's activation by other hormones, low hormone levels in the blood, and also stimulation by nerve impulses. Let's start off by looking at what happens when endocrine glands are activated by other hormones. And here is an illustration of a great example of anterior pituitary gland and downstream hormones. Okay, so here, this is actually the anterior pituitary gland over here. Okay, so this is the posterior. And how do we know this is anterior? Well, anterior pituitary secretes three different types of hormones that regulate the activities of these downstream glands. And so let's see what exactly this looks like. So anterior pituitary gland is to secrete their hormones, or its hormones, all here in red. And that in turn is going to target either the thyroid gland, adrenal gland, or gonads. And this in turn, once these hormones hit these organs themselves are going to secrete their own hormones downstream to have some sort of physiological effect. And so anytime one endocrine gland causes the second endocrine gland to secrete their hormones, this initial hormone that initiates all these reactions to occur are called tropic hormones. So tropic hormones are hormones that target a second, so they target an endocrine gland to secrete their hormones. Okay, so great example here. Anterior pituitary gland secreting thyroid stimulating hormone, TSH. That's going to target thyroid gland. Thyroid gland is going to release calcitonin, or a thyroid hormone. Another way we can stimulate the hormones to release is by changing the blood levels of certain ions, and that in turn is going to stimulate these hormones to be released. Great example is parathyroid hormone and calcitonin. Both of these hormones are antagonistic to each other, meaning that they work in opposition. And what they do is they both regulate calcium levels within your blood. So parathyroid hormone, what this is going to do, this is going to increase blood levels of calcium. Calcitonin, just like it's in its name, it's going to tone down levels of calcium. Okay. So both of these are going to, so in the event that there's low levels of calcium, the thyroid gland is going to receive that signal. It's going to secrete which hormone? So low levels, it's going to release parathyroid hormone. Parathyroid hormone in itself is going to work on your bones in order to start breaking those down to release calcium levels, and in turn it's going to shut off that stimulus of having a low calcium levels in your blood. Third way we can stimulate hormone release are by nerve impulses. Most of these are under the control of the sympathetic nervous system, and is that the fight and flight or the rest and digest? Good, it's that fight and flight. System, and that's going to release norepinephrine or epinephrine by the medulla. Now we're going to move on to looking at all the different types of endocrine organs, and we're going to go over each type of hormone that they secrete and also the functions of those secretions. Great thing to look at for your exam is an overview, this entire page. You can have for your third exam an illustration of the organ. I can be pointing out to the structure and asking you to identify that gland, or I can also point to the structure and say, which of the following is a hormone secreted by that gland, or which is a function of one of the hormones secreted by one of those glands. So definitely know the gland, the hormone, and then the function of each of those hormones. We're first going to start off with the hypothalamus and the pituitary gland. Hypothalamus, this controls your body temperature, your hunger, thirst, fatigue, sleep, and circadian cycles, so sleep-wake cycles. And we have found within our hypothalamus a bunch of neurons called neurosecretory cells. And they're going to influence both our posterior and anterior pituitary glands differently. Now, we also can say that our hypothalamus is pretty much the in-between or relay station between our central nervous system and our endocrine system, because our hormones can be released and triggered to be released by our hypothalamus by our central nervous system. And our hypothalamus, in turn, pretty much controls the activity of our anterior pituitary gland, which in itself controls many other hormones. And this is why we call this that relay station. Now here is our hypothalamus. It's connected to our pituitary gland by what's called the pituitary stalk. We have this posterior pituitary gland, which is directly connected to our hypothalamus, so direct connection. And we have the anterior pituitary gland. Now, because the hypothalamus is directly attached to this posterior pituitary gland, we can start generating, so we can produce hormones within our hypothalamus that are stored in the posterior pituitary gland. And because they are directly connected, we have direct interaction. However, since our anterior pituitary gland is not directly connected to our hypothalamus, well, we have our capillary beds that help join them through that communication. So they can communicate through capillary beds. And it's secretion by certain proteins and components by hypothalamus that triggers and initiates activity of this anterior pituitary gland. Now let's look at the structure here. This is called neurosecretory cells of the hypothalamus. We saw that in the last page. And here is what allows us to have that direct connection between our hypothalamus and our posterior pituitary gland. And as I mentioned, hypothalamus is going to produce hormones that are stored by our posterior pituitary gland, and that way we can call posterior pituitary gland an endocrine gland, because it secretes the hormones generated by the hypothalamus. So posterior pituitary in itself does not, so I'm going to write this down for you because this is key, posterior pituitary gland does not generate or synthesize hormones. It only secretes them. So secretes and stores them for the hypothalamus. Now hypothalamus generates two different hormones. We have antidiuretic hormone, which we abbreviate as ADH. And we have oxytocin, and both of those, once produced, are going to get stored within our posterior pituitary gland. And the functions for these are twofold. So anterior antidiuretic hormone, this is going to target our kidney tubules to cause water to be reabsorbed within our kidney tubules. Now, what happens? This is going to allow increased blood pressure, and also in turn will eventually cause increased blood volume. This is also called vasopressin. Okay, because in large amounts, antidiuretic hormone can cause vasoconstriction. Now, second type of hormone we have is oxytocin. Oxytocin is going to target our mammary glands and also uterine muscles. This is going to eject milk during nursing, allow contraction of the uterus during labor. So this is, remember that one example of being that positive feedback. And also, Oxytocin is responsible for orgasms. Looking at the pituitary gland, this is the size of a pea. It has two functional lobes that we just saw, anterior pituitary gland and posterior pituitary gland. Anterior, we call it glandular tissue because in itself it's producing these hormones and it can secrete them. And it's not under the control of that nervous system, whereas that posterior pituitary gland, it's not directly connected to that. It is directly connected to that hypothalamus, which is why we also call it nervous tissue. It also has those neurosecretory cells stemming from it, which is why we also give that term of that having that nervous tissue. Now, pituitary gland in itself, we often call it the master gland, and this specifically refers to your anterior pituitary gland because it controls the actions of so many downstream organs, and we'll see that in a little bit. Okay, so hormones of this anterior pituitary gland. What's characteristic of all the hormones that are secreted from this is that they're all proteins. And so because these hormones are proteins, what type of system are they going to act when they get downstream? Or is it going to be direct gene activation, or it's going to work through second messenger systems? Good, so it's going to act through that second messenger systems. And most of these are going to be regulated by hormonal stimuli that are going to be negative feedback. Very few times will you ever get positive feedback. Now here we have all the different types that we're going to be looking at. So anterior pituitary gland, once again connected indirectly to the hypothalamus, and we can connect them only by these blood vessels, so capillaries stemming and spanning from your hypothalamus down to your anterior pituitary gland. And because we don't have that direct activation and direct, we do have direct activation, but not direct interaction, we have two different types of secretions from our hypothalamus that can enter into this capillary bed. The first one we have are releasing hormones. And these are actually produced by the neurosecretory cells. Here's our hypothalamus, here's the posterior pituitary. Here are those neurosecretory cells. They can secrete, while they have this direct interaction, they can secrete these hormones that enter into the capillary bloodstream of your anterior pituitary gland that can target and trigger the anterior pituitary gland to secrete all these different types of hormones. So it can cause releasing hormones, in which case it's going to stimulate the anterior pituitary to secrete hormones, or it can produce inhibiting hormones, in which case it's going to prevent the anterior pituitary from secreting hormones. Okay, and really this underlies the reason why this anterior pituitary is the master gland, is because once it's inhibiting or causing the release of hormones, it can target your growth hormone, looking at your bones and muscles, prolactin targeting your mammary glands, FSH and LH targeting your reproductive structures, thyroid stimulating hormone, that's targeting your thyroid, adrenocorticotropic hormone stimulating your adrenal cortex. And the way I know there's lots of different types of hormones that you'll really need to know. However, the way I like to remember things are by, once again, creating phrases or acronyms. And the way I remember this is by M-FLAT-PEG. Now, M is something, and E you don't need to know. So that's for melanocyte stimulating hormone and also for endorphins. These are not covered in your book, so you don't really need to know these. However, for F and L, this is follicular stimulating hormone and luteinizing hormone, targeting the gonads for the production of sex hormones and control the menstrual cycle in females. You have A for adrenocorticotropic hormone, targeting your adrenal cortex for the production of glucocorticoids. You have T for that thyrotropic hormone, so that's going to be, or also known as your thyroid stimulating hormone, targeting your thyroid gland. P is for prolactin, causing your mammary glands to lactate. And then G for growth hormone. You're going to both target your liver, free up all that glycogen stores for glucose because you need that energy for your growth of both your muscles and your bones. Now we're going to look at this anterior pituitary gland, looking at each of those hormones, starting off with this growth hormone. And it's going to target your skeletal muscles and your long bones. And because with this is continuously active, this in turn is going to determine your final body size. All those amino acids are going to be built into proteins, and we're also going to cause the breakage of those fats and use it as an energy source. And here's a quick reminder of your chapter 5, how our bone is going to grow. Here we have if this is a child, we have, what is this? Good. That's going to be that epiphyseal plate composed of hyaline cartilage. We need all that mitotic activity, those growth hormones, stimulate mitotic activity, this hyaline cartilage. Grow and divide, that's going to cause this to grow this way. And also mitotic activity for your osteocytes to replace all this hyaline cartilage with that bone. Lots of energy needed for that. And we can have longitudinal growth because of this. Now looking at more bone growth, because this is going to be especially found in growing bones, bones are always going to be remodeled and lengthened until your growth actually stops. And remember, remodeling deals with its continual breakdown and reforming of your bone tissues. We're always going to reform bone, break it down due to calcium levels, and also pulling on your bones due to stress. And so we need to have both appositional growth, side to side, especially for pulling on your bones without muscles, and longitudinal growth when it comes to especially this epiphyseal plate. Now, other tropic hormones that we have, we're going to look at the tropic hormones that we have for our pituitary gland. We have adrenocorticotropic hormone targeting your adrenal cortex. A lot of time we're going to look at stress. We're going to see that next video lecture. Then thyroid stimulating hormone. This is for both metabolism and calcium levels. Another one we didn't look at here is prolactin. Once again, stimulating milk production, childbirth. We also have this in males, but the function in males are not known. Gonadotropic hormones, this is going to regulate the gonads. FSH, follicle development found within the ovary, so all of those oocytes that are eventually going to form and help develop the surrounding tissues of those oocytes. Sperm, also found within the testes. Luteinizing hormone, this is going to trigger ovulation of an egg in females. And then testosterone production within the males. Okay. And now, a lot of times, a lot of this feedback is going to be negative. And why is that? Well, you want to maintain control. Imagine what can happen if you have too much stimulation of these hormones. You're going to have disorders. And so really that's the reason why all of these hormones are controlled by this negative feedback system. You remember if you remember having this balance beam, the moment one thing is too high, you want to regulate it to bring it down. You want to maintain that balance. Same thing if you have too low of a hormone, you want to raise it up to maintain this balance. And so we can stimulate endocrine glands from other glands to eventually shut it off, which is why we have this negative feedback. So a lot of times you're going to see a lot of these hormones being antagonistic to each other to maintain that homeostasis. So you always want to avoid hormone imbalance and avoid overproduction of a hormone. Now what can happen if this is not regulated? You can come up with disorders. One disorder we're going to look at, or a couple of disorders from growth hormones, you can have pituitary dwarfism. This can result from hyposecretion of growth hormone, and this occurs during childhood. So hypo meaning too little, so too little secretion. What's going to happen? You're not going to encourage the stimulation and growth and development of those epiphyseal plates. You're not going to have longitudinal growth of your bones, and you're also not going to have appositional growth. So what happens, especially during childhood, if that doesn't happen, your bones are going to remain very short. Gigantism, what's going to happen? This is hypersecretion of growth hormone during childhood. So overproduction of growth hormone, increase in lots of longitudinal growth as well as appositional growth. Now what happens, and also gigantism occurs because you still have those epiphyseal plates. Now what happens when you have an epiphyseal line but you're still stimulating the growth hormone production? So that can result in acromegaly. So this is hypersecretion during adulthood. And here is a normal adult male. And here is a patient who has acromegaly. And what you'll notice is because here we have our bones, we had our epiphyseal line within adults, right? We don't have any more growth there. The only way we can grow is appositionally, so growing side to side. And so what happens when people with this is their muscles, I'm sorry, not the muscles, well, muscles too. Muscles and bones are going to grow. Specifically, bones are going to grow appositionally, so they're going to grow much wider, much denser. Here's an example of a couple of people who have suffered from pituitary dwarfism, gigantism, and here's a normal height woman. So gigantism, once again, overproduction of growth hormone by a pituitary tumor. Here's Robert Waldo, tallest man, Guinness Book World Record at 8 feet 11 inches. When he was only a teenager, I think he was only, not even a teenager, less than a teenager, he was like only 10 or much younger than that. He was already 5 foot 4 inches. Can you believe that? So he's already taller than me when he was only 10 years old. Crazy. Now, this, I know you all are going to pay attention to this because this has probably happened to all of you. Well, I shouldn't say all of you, but a good majority. No judgment, right? Because this, of course, happened to me too. And this has to deal with antidiuretic hormone. Now, antidiuretic hormone, let's write this down. What does this do again? It causes water to be retained. So we're going to increase water reabsorption in the collecting ducts of our kidneys. So kidney nephrons, we're going to get into that structure within our kidneys. Now, because antidiuretic hormone, this is going to increase water absorption, we can increase our blood volume, increase blood pressure. What happens when you drink alcohol? Well, we have something called ethanol found in alcohol. And what that's going to do, it's going to inhibit the release of antidiuretic hormone from which pituitary gland is this again? Anterior or posterior? Okay, it's from that posterior pituitary gland. Now let's think about this first. Under normal conditions, you're going to secrete antidiuretic hormone. You're going to increase water retention. Alcohol inhibits antidiuretic hormone from being secreted into your collecting ducts. Therefore, no antidiuretic hormone. You're not going to release if no antidiuretic hormone, what's going to happen to your water? Your water is going to start coming out. And so what happens when you drink lots of alcohol? You're going to produce lots of dilute or concentrated urine. Lots of dilute urine because a lot of that water is going to be coming out. Now, especially for you women, you know, going to the clubs, going to the parties, what happens? All those long lines in the women's restrooms, right? All that alcohol causing this inability to retain all that water. And so really what happens the next day? Well, if you don't continue to drink water, you keep using that restroom, you keep drinking lots of alcohol, that's going to leave you dehydrated, and that in turn is going to lower your blood pressure, giving you rise to that nauseous feeling that you have. And what do we know this as? That hangover. Yep. And hopefully you don't end up doing dumb stuff like what these guys did and winding up with a baby. Right. So what do you do and how do you resolve this? Well, that's why the people tell you take electrolytes. Very important. You want to drink Gatorade or even vitamin water. Any water that has electrolytes in it. And why is that? Well, you know now from, here's your blood vessels. If you drink lots of electrolytes, you're going to have lots of those ions, sodium, chlorides found here within those liquids. That's going to cause and force, if you have a high concentration here also, it's going to force you to maintain both water in and out of your cells. Okay, you're also going to allow more water to circulate within your blood vessels because you have all those electrolytes found here within your blood vessels. Okay, so very important to hydrate. Now, next gland we're going to look at is the thyroid gland. Thyroid gland, this is found at the base of your throat, and it produces two different hormones. We have the thyroid hormone and the calcitonin. We have these two, it kind of looks like two different lobes, and it's connected together by what's called the isthmus. We're now going to look at the two different types of hormones secreted by the thyroid gland, starting off with the thyroid hormone. And we notice as a metabolic regulating hormone. And over time, what happens? Well, a lot of people have a decrease in their metabolic activity, and because it's a decrease in the percentage and amount of thyroid hormone being produced. There's two different forms of thyroid hormone in our body. We have thyroxine. Thyroxine, this is also known as T4. This is a major circulating form in the blood, and in order to produce this, we need iodine. Now, this is an inactive form of the thyroid hormone. Triiodothyronine, this we know as T3, this is the active form of the hormone, and this happens once T4 will bind to the target tissue, target site, and get converted to this T3. So it gets converted and activated at the target site. Now, what produces thyroxine is follicle cells. And so here are the follicle cells right over here, surrounding what's called a colloid-filled follicle, meaning all of this found in here is filled with all of those hormones. Now, one thing that can happen if we don't maintain homeostasis of these hormones are the formation of goiters. And this forms as a development due to a lack of iodine. Let's take a step back and see what happens. Now, you remember, these hormones are going to be synthesized and stimulated for their production if there is not enough of these hormones systemically. And so what happens is, in the event, let's say here we have normal levels, we don't have too high, we don't have too low levels of T3. So what happens now, let's say that in the event we don't have a lot of levels of T3, so T3 is low. What do you want? You want to stimulate the production of T3. How are you going to stimulate the production of T3? Well, this is the activated form, so you need to take a step back. You need to produce more T4. How do you produce T4? You produce T4 by the presence of iodine. Now let's say, okay, so in order to produce T3, you need T4. So let's say somebody, especially this happens in third world countries, you don't have a lot of iodine. So what happens? You don't have a lot of iodine, but you need T3. So your body is going to start sending all of these signals to stimulate your follicle cells to secrete T4. So stimulation for your follicle cells to secrete T4. And why do you need that again? Because you need T3. So what happens? Let's see. Stimulate this, you need that. Now in your body you don't have any iodine. So if without any iodine, that in turn you can't produce T4, no T4, no T3. But your body still needs T3. So what's it going to do? It's going to start sending an even larger stimulus. Well, we need that T3. We need that T3. So what are you going to do? You're going to encourage more follicle cells to grow and divide. Why are you going to stimulate this? Well, you want more to grow and divide because you need this T4. But you still don't have any iodine. So what's going to happen? You're still going to cause this to continue to be, well, maybe if I stimulate and cause a division of more follicle cells to continue to grow and divide, eventually I'll get T4. Well, that still doesn't happen. But over time, what happens? Here is your thyroid gland. You're stimulating more follicle cells to be produced because you're hoping that you're going to produce more T4 in order to generate more T3. You still don't have any of that iodine, so what happens? Your follicle cells continue to grow and divide, and continue to grow and divide. And over time, what happens is you have this enlarged thyroid gland because you don't have enough iodine. Well, how do we prevent that? We can prevent that by, a lot of people eat salt, so you can iodize salt, and that'll give you enough iodine needed in order to maintain your T4 levels, and therefore maintaining your T3 levels. And so a lot of times in third world countries, you're going to see people with enlarged thyroid glands because they lack iodine, and they're continuing that stimulation to produce your T3 hormone. Okay, so once again, all that idea of homeostasis. If you don't have enough of that hormone, you're going to keep on sending those signals to stimulate more hormone production until you get enough hormone within your body. Cretinism, this is caused by hyposecretion of thyroxine or T4. This is going to result in dwarfism during childhood. Now, why is that? Once again, metabolism, encouraging the breakdown and storage of all of these different proteins and fats and your glucose molecules. Another homeostatic imbalance because of this hormone is Graves' disease. This is caused by so excessive thyroidism, increased metabolism, heat intolerance, rapid heartbeat, weight loss. Also, what's characteristic of someone with thyroid or Graves' disease is protrusion of the eyes. Second type of hormone secreted by our thyroid is calcitonin, and this is secreted by what are called parafollicular cells. Here is the follicular cells directly surrounding that colloid mass. In between, you're going to see the space, and all these cells in between the space, those are the parafollicular cells. So all these in between. These decrease calcium levels, and therefore, because it works in opposite to increasing calcium levels, this is antagonistic to your parathyroid hormone. The next endocrine gland we're going to look at is the parathyroid gland, and this is going to secrete the hormone parathyroid hormone. Now, what's this going to do? It's antagonistic to calcitonin, meaning it's going to increase blood levels of calcium. Parathyroid glands, you can notice this as 4 small glands. On the opposite side of the thyroid gland, it's going to stimulate osteoclasts to remove calcium from the bone. Remember, in order for us to increase blood levels of calcium, we're going to break bone, and osteoclasts will crush the bone to free up all that calcium. We can also stimulate the kidneys and intestines to reabsorb all that calcium, and finally turn off that stimulus of having low calcium levels. Here's this overview of how calcitonin and both parathyroid hormone work together. And here is this example of normal levels. We have 9 to 11 milligrams per 100 milliliters of blood calcium. And this is our normal homeostatic parameters. But in the event that there is too much calcium, what are we going to do? Thyroid gland is going to release calcitonin to tone down calcium levels. So in order to tone down calcium levels, you're going to increase the amount of calcitonin. This is going to stimulate osteoblasts to build all that bone and deposit all that calcium within the bone. Eventually, over time, we're going to have homeostasis. Now, in the event that we have too little calcium, we're going to stimulate parathyroid gland to secrete parathyroid hormone. Parathyroid hormone is going to get increased. Then we're going to stimulate osteoclasts to crush all that bone to free up all this calcium, and then in turn we can maintain our calcium levels, our normal calcium levels. And of course, if we're crushing bone and dealing with this calcium, very important to drink or take in your calcium, enough calcium so you don't start damaging your bone, especially in older women who can suffer from osteoporosis. Alright, so this is the very last slide we're going to cover for the first part of Chapter 9. I'll see you in the second part of Chapter 9.